Greetings and welcome to my new calculus channel. My name is John Gabriel, and instead of going straight over into book 3, I'd like to just talk about one more example or proposition in book 2 and show you how you can learn to study these propositions in Euclid's Elements and point out a few other things along the way. So let's begin. Now, in proposition 4, we see what Thomas Heath calls very cheekily, he says this proposition is a geometric version of the algebraic identity. I'm very sorry, but algebra came after geometry, and the algebra is a weaker form of geometry, and this identity actually comes from geometry. Now you'll see later on that in geometry we never have a problem with this type of operation, but in algebra we can, because algebra allows 0 to assume number status. Okay, so without further ado, let's see how you can learn how to study the propositions on Euclid's Elements. So before I start, some of you might want to know how to read and learn the original Greek. So the original Greek that you'll see on this side here of proposition 2, actually it's all this on the side here. Okay, so this is the statement, the original Greek, is written in something called katharevousa, which means something like a clean Greek or an original Greek. And it's got all these little accents and marks, etc. Now, if you try to put this into your Google Translate, excuse me, like you do here, you'll see it can't translate it because Google only translates modern Greek. So if you want to know what that is saying, what you need to do is replace all these letters without the accents, as I've done here. So for example, you'll replace that one simply with, let's say, a U, okay? I mean an epsilon. So you'll put an epsilon like that, and then you'll put an accent. The only accent allowed in modern Greek is the one that leans towards that side, okay? So, and of course, the one that you want there is this one, and the first one is this one. Okay, so if you get rid of all that, because I don't want it all to be there, now suddenly you've got something which seems like something that makes sense. Okay, so if a straight line, and of course that there also in the modern Greek is written that way. Okay, so that means if a line, if a straight line. Okay, so and the way you can do it is like this. Now of course that doesn't guarantee you're going to get a good translation, but it gives you a rough idea of what the proposition is saying. Okay, and that's geared towards those of you who are wanting to learn Greek or to study the elements in the original Greek. I'm not going to bother with that anymore. Now let's look at example 4, which states that if a straight line is cut at random, that's very important, then the square on the whole of the straight line is equal to the sum of the squares on the pieces of the straight line and twice a rectangle contained by the pieces. And the reason I'm covering this is that in my previous video I talked about proposition 12 in book 2, which is a kind of a forerunner of the cosine rule, and I wanted to show you how this leads up to that proposition. Okay, and that's why I chose it. Now this isn't a particularly hard one, and if you're using something like a mathematical algebraic software like Geogebra or MATLAB or any of the others, Mathematica, the way you should do it is as follows, and I'm going to show you how to do this in steps. So the first step is if a straight line. So if you want to have a straight line, you'll basically create your straight line in your software package and you'll do nothing else. And you want to be able to move it, right? So you want to be able to move the line. So it's important that you do this in the right order, because if you don't, at a later stage, if you try to vary any of the points, you'll have something that may not actually resemble the original proposition. In fact, it will look as if the proposition hasn't worked, perhaps. So if a straight line is cut at random, it means anywhere along this line, right? Then the square on the whole line AB, the whole line, the square on the whole line, yes, is equal to the sum of the squares on the pieces. So the pieces AC and CB. So this here is the square on AC, and this here is the square on CB. And it doesn't matter if it's halfway either, because that's true as well. And it's easy to realize this by drawing a diagonal. And so it says if it's equal to the sum of, it is equal to the sum of the squares of the pieces AC and AB, and twice the rectangle. So twice this rectangle or this one, because they both happen to be equal. In other words, AC times CB, meaning the conclusion, which is this, right? So very simply it says that AC plus CB, the whole line squared, is equal to the square on AC, this is the square on AC, plus the square on CB, plus twice the rectangle formed by AC and CB, okay? So that's the conclusion. Now, in algebra, if we take another statement, which is also true, this is also true in the geometry also, but in algebra you could run into problems with statements like this. So for the above equation, which is true, algebra reflects a geometric identity, but not vice versa. For starters, you cannot apply this to a straight line divided in half. Why? Because then you'd have 0 squared. And of course, if A happened to equal to B, which means it's a straight line divided into 2, then you cannot divide by A minus B, because there's no such thing in geometry. Geometry deals with magnitudes of length, not numbers, okay? Whereas algebra, a weaker form of geometry, deals with the abstract unit. In other words, algebra attempts to talk about lengths of magnitudes or volume or anything else in terms of the abstract unit. So in algebra, something like this is exactly the same. 3 pi squared over pi is equal to 3x squared over x, because both x and pi are symbols for magnitudes. Pi is decidedly not a number. It's a symbol for a magnitude, okay? In fact, a ratio of magnitudes. Not even a magnitude on its own, but a ratio of magnitudes. Now, 0 equals 0, which leads to so many contradictions in algebra, is not possible in geometry. So you cannot have the scenario in geometry. And because algebra allows this, if one is not careful, one can end up with illogical conclusions, such as 1 equals 2 or 2 equals 5. So let's see an example on the side here. So if you say 0 is equal to 0, which you cannot do in geometry because there is no such thing as a 0 magnitude, then of course you have 20 minus 20 is equal to 25 minus 25. And of course 20 is equal to 4 times 5. So you can go ahead very nicely and write down the third line, and you can factorize each side as you see in the fourth line. Until here you don't have a problem in algebra. But the minute you try to divide by 5 minus 5, or cancel it out as a factor, you get something which is total nonsense, okay? Because 4 is not equal to 5. And in geometry, this never happens because 0 is not a magnitude, okay? In fact, 0 is not even a true number. It's just being given special number status. So, as you know, in the first few books, the propositions don't even deal with numbers. They deal with magnitudes. In other words, lengths, which have no particular measure. They're just related to each other, either in terms of length or in terms of area. So you'll get geometric objects which are equal because they're equal in area or they're equal in length, but never in number. Number only comes along in book 7, and that's quite a way off. But before book 7, we have book 5, which actually establishes all the operations of arithmetic, which of course algebra inherited from geometry, okay? So it didn't happen the other way around. Algebra inherited the operations of division, subtraction, division, multiplication, and addition from geometry. And all the stuff, all the things that you do in algebra with fractions. In other words, when you say multiply a fraction by another one, you multiply the numerators and the denominators, and then you cancel out. All that stuff is possible because it's how it happens in geometry, okay? Some idiot professor, mathematics professor, didn't just say, define A over B times C over D to be equal to AC over BD. That's absolute bullshit. It doesn't work that way. Mathematics is not about defining whimsical definitions like most mainstream mathematics professors do, because they're idiots, okay? And they've never understood mathematics. In fact, they've never understood Euclid's elements and have never understood geometry. In fact, Euclid's elements is not about geometry. Does that come as a shock to you? Well, you can study my work and my previous videos and you'll see that Euclid's elements is not about geometry or about constructions or any about the nonsense that the morons in mainstream academia have been propagating over these centuries because of their total ineptitude in mathematics. Okay, but I do know better than all of them, and I'm teaching you these things, and so you have a chance to be smarter than all those fools and not become as one of them. So I'm going to stop here because I can probably carry on with this in another video or talk about another interesting topic in the not too distant future. This is a new calculus channel. My name is John Gabriel. Till next time, goodbye.